Okay, so this is the differential equation, correct? What we can do, we can write it in the standard form as last time. First, to test if it's exact. So we're going to move this x over. So then we get 1 over xy minus x equals, or plus, dy over dx equals 0. So this is in the standard form as last section. And if you remember, this was our m, and this 1 here that multiplies the derivative was our n, wasn't it?
Yeah.
And then it's exact if and only if dm over dy is equal to dn over dx. Partial derivative of m with respect to y equals partial derivative of n with respect to x.
Yeah. Right.
So then we can find out what those are and see if it's exact. Right? So dm over dy, partial derivative of this with respect to y is 1 over x, and partial derivative of n with respect to x is 0, because, you know, the derivative of a constant is 1. So therefore it's not exact. So that means we need to make it exact.
Yeah.
Oh, and by the way, I moved the x to the left. I could have kept the x on the right and tested for it, you know, in the regular standard form, 1 over xy plus dy over dx, to see if it's exact.
Yeah.
But either way, my point is it's not exact.
Yeah.
Right? So now we have to make it exact. So let's go to the original question. That one there. So this is 1 over xy plus dy over dx equals x. Okay? And so to make it exact, we need to find an integrating factor.
Yeah.
Okay? And let's assume this integrating factor is some mu prime. Yeah. Well, the derivative of the integrating factor is some u.
Yeah.
Then we can multiply here by this, by the integrating factor, and here by the integrating factor. Okay?
Yeah.
Now, this is the trick, is where you can say, well, this is the partial derivative of x of, well, dy over dx will be y times your integrating factor, which is mu, such that if you do the product rule on this, you would get the first one. Right? So partial derivative of y is dy over dx times mu, plus y times the partial the derivative of mu, which should be this, equals mu times x. Now let's FOIL this and see where that gets us. So I show you what I'm saying. If I were to do the product rule on this again, I would get d mu over dx times y. You follow?
Yeah.
Plus, so the derivative of mu times the second as is, plus the derivative of the first, which is dy over dx, times mu as is, equals mu of x. Okay, let me show you what I'm saying. Compare this with this. You have y here and y here. You have dy over dx here, and you have dy over dx here. You have mu here, and you have mu here. That means, and you have mu x here and mu x here. So that means the last one has to agree with the equation, which means from these two, I can then claim that mu over x, mu times 1 over x, has to equal d mu over dx. And now I can solve this for mu, which is my integrating factor. Because these two have to be the same.
Yeah.
For this to work.
Right, I got it.
Separate the variables. So you get, of course, d mu and dx have to be on top. So you get cross multiply here, and you get mu dx equals x d mu. Separate the variables accordingly. So divide both sides by x and both sides by d mu. So we get by mu, I mean. So we get d mu over mu equals dx over x. And integrate both sides. So now I can integrate here, and I can integrate here. Integral of d mu over mu is ln mu. This is starting from scratch without assuming any formula or using any formulas or making any assumptions.
Right.
You're trying to multiply the differential equation by something such that when you go backwards with the product rule, you actually get the original differential equation.
Right.
And there you can find what that integrating factor you need is. So then we get ln mu equals ln x, because integral of dx over x is ln x, which means mu has to equal x. So our integrating factor is, so we've arrived at our integrating factor is actually mu equals x. And now we go back and we do what we initially intended to do. We multiply the entire equation by mu. So then we will get, when we multiply equation, star or this one by mu, 1 over x times x will give us y. Let's use another color here. Okay. And then, the second one is mu is x, we said, so plus x dy over dx equals x squared, because the right hand side now is x squared, x times x.
Yeah.
Okay, and again, now we can couple these as we did. So just like we did, except we're plugging in now. So this is the same thing as the partial derivative of x times y. You agree? Because derivative of x is 1 times y will give you y, the first term, plus product rule, the derivative of the first as is x times derivative of y dy over dx. Bingo, so you get this. Equals x squared.
Right.
And now we can multiply both sides by dx, separate the variables. Or actually, no, let's so now we can integrate both sides.
Yeah.
Here, at this point. So let's do that. So we put an integral sign here and an integral sign here. And as you know from fundamental theorem of calculus, if you take the integral of a derivative, they just go away.
Oh, yeah.
And you just get xy out of this. Equals integral of x squared is x cubed over 3. Oh, by the way, this dx can go and sit here now, right?
Yeah.
So you get integral of x squared is x cubed over 3. Right? So so then we can divide both sides by um, plus c, right? And we can move one term to the left, and now we get our family of curves, x, y, minus x cubed over 3 equals c. And we were able to solve, even if it's not exact. By the way, at this point, you can test if it's exact. We know it has to be exact because, you know, the product rule works.
Yeah.
But in any event, whether it's exact or not, I don't really care because I didn't use so much the fact of the gradient being partial of, and you could do that if you want, but I didn't use this fact. I just used separation of variables at this point. At this junction, once you get your integrating factor, you can go one of two ways. You can either continue doing what you've assumed and use separation of variables, or you can use the exact solution by figuring out, you know, the potential whose gradient is and work it out. Either way, you'll get the same answer.
Right. Exactly. I got it.
Right. That's the factor that's why it's called integrating factor.
All right. All right.
So that does it for that problem. You want to attempt one on your own?
Yeah.